Now here is another reminder. We know that when we're dealing with linear forces, work is equal to the integral of that force with respect to distance. We can do the same thing in a rotational sense. Say that work is the integral of torque with respect to angular distance. If torque is constant, that just becomes multiplication. Work equals torque times angular displacement. If we take a derivative of that equation with respect to time, well, the time derivative of work, the rate at which work is done, is power. And with a constant torque, we're taking the derivative of angular position. That gets us angular velocity. And this is our formula for instantaneous power. We can use it's equal to torque times angular velocity. You may recall that a formula for power we used was force times velocity. So torque times angular velocity, it's the same pattern. And a reminder, work kinetic energy theorem says work net equals change in kinetic energy. So if that work happens to be causing rotational motion instead of translational motion, then we could write work net equals change in kinetic energy, which is 1/2 I omega final squared minus 1/2 I omega naught squared. So it's the same, analogy isn't even the right word. It's the same formula, but if the kinetic energy involved is the motion of a rotating object, then we can use 1/2 I omega squared instead of 1/2 mv squared. So we just have a couple examples here. Now that we know how to deal with the energy of a rotating object, that means we can apply conservation of energy to things involving rotating objects. So here we have a rod, length m, L, mass m, attached to a frictionless pivot. It's attached to the ceiling. It's initially pressed against the ceiling and then released. So it starts here, rotates down, and at some point later, it's hanging down vertically at its lowest point. We want to find the angular speed of the rod when it reaches that point. Well, in this case, gravity is the only thing doing work on the rod, and gravity is a conservative force. So we know that that mechanical energy for the rod is conserved. So we can say initial energy equals final energy. So initially we have some kind of potential energy. Remember, gravitational potential energy on Earth, we can say, is just mgh. But this is a little bit tricky for the rod because different points on the rod move a different distance down. But as a general rule, we will use the center of mass as our height for the gravitational potential energy, because that's accurate. That is the average height of all the mass. So if we want to set our 0 for potential energy where our rod winds up, we can put our 0 for potential energy at the center of mass of the rod. And then our initial potential energy would be equal to mg times this distance, which is half the length of the rod. That's what we start with. Down at the bottom here then, our potential energy is 0, and we have some kind of kinetic energy. Since our rod is rotating, we call that 1/2 I omega squared. For a rod with an axis through the end, we know that our moment of inertia is 1/3 ml squared. And then we can go ahead and do some algebra to calculate the angular of our rod. Masses cancel out, factor of L cancels out, or half cancels out, and we're left with omega is square root of 3g over L. Now if we wanted to find tangential speed, it's pretty simple. Just remember tangential velocity is equal to r omega. So the lowest point on the rod is a distance L from the axis of rotation, so that's just L times root 3g over L. L over root L equals root L, so we can simplify that to square root of 3gl. Just another example. A modified Atwood's machine has a mass of 3m at rest on a frictionless table, and a hanging mass, 2m, attached by a string that runs over a pulley. So our system looks like this. It's approximately disc-shaped. It has a mass m, radius r. The string does not slip on the pulley. hanging mass is initially a height h off the ground. We want to find the speed of the system as it hits the ground. Well, our initial potential energy is just mgh. The only thing that's changing its potential energy is 2m, so initially we have 2mgh as our potential energy, and then that's all translating into kinetic energy. 2m and 3m have normal linear kinetic energy, so that gives us 1/2 2mv squared plus 1/2 3mv squared, and then the pulley is rotating, so that has rotational kinetic energy. This comes out to 5/2 mv squared, and for our pulley, we said it's approximately disc-shaped, which means its moment of inertia is 1/2 mr squared, and we know the angular speed of the pulley is equal to v over r. So r's cancel out. We wind up with 5/2 plus 1/4, which is 11/4 mv squared on the right side, 2mgh left side. Masses cancel out, and multiply by 4 over 11, we get v equals square root 8 over 11 gh. That would be the speed of the system as the mass hits the ground. If we want to find instantaneous power, we just learned that power is equal to torque times omega. Well, what's the net torque on the system? The only net external force in the system is the gravitational force on 2m. So that force is 2mg. That acts a distance r from this axis of rotation of the pulley. So it's 2mgr times omega, which is v over r. So that's root 8 over 11 gh over r, which isn't very pretty. Notice this is the same thing as force times velocity. That's interesting. And this equation doesn't look very nice, but whatever. We'll just leave it as it is. So the instantaneous power is 2mg times square root 8 over 11 g